Hello, my name is Jung from University of Minnesota, and this is a collaboration with the U.S. National Forest Service. So let's say you're a historian studying structural difference of a building from the past, and using gathered data, you can create this realistic model of a building, and you can use your desktop to see it. Or using VR, you can immerse in the data, and then why would you do that? This reminds me of a story of our colleague who is a historian studying this historical site in ancient Greece where people gather here to give a speech. And he had this architecture model for about 6 months, and he had been using and working on the desktop. And within 5 minutes of using VR to see the same model, he realized there's a problem in the model where the scale of a key architecture feature was off by a factor of 3. The data that involves in body-centric real-life scale analysis, virtual reality provides a really powerful tool. But in most cases, you might have more than one building. This is not just for historians, but architects, scientists comparing multiple sets of simulations. Comparison is the crucial data analysis task. In desktop, one thing you can do is to put them side by side and compare. The benefit of this approach compared to going through one by one is that you don't have to rely on your memories to make comparison. But how we do this kind of comparison in virtual reality? So our driving research question is to given the data where each data instance is a virtual world at a real life scale, how do we simultaneously compare them? So virtual reality provides unique additions to analyzing data sets. Even though comparison is a crucial data analysis task, it's not well understood how to do that in VR. So according to a recent survey, Keefe et al. Points out there are 4 approaches of comparing 3D models. Interchangeable approach, you show one by one. Juxtaposition, you show side by side. Superimposition, you overlay them. And the explicit encoding, you only show the differences. The point of this table is to show that there's no one perfect solution. Each one has advantages and disadvantages. According to the same survey mentions, there are only 2 papers that does comparison in VR. If we dig more, we might find a few more. But I think the point is that doing comparison in VR is not well understood topic. And this is a problem because if we were to use virtual reality for data analysis, we need to understand how to do this. So one approach is interchangeable approach. You immerse in one world at a time and click a button, go to the next one. Problem of this approach is that you have to rely on your memories to make comparison. Juxtaposition approach addresses this issue. Keefe et al. Takes this approach, but his case only works for small objects. Our approach works for large objects like terrains. So how about these 2 other approaches? The reason for us going to the juxtaposition approach first is that because it's the most generic approach. For instance, in order to do the superimposition approach, the data needs to be co-registered, unless overlaying them wouldn't make any sense. And then for explicit encoding, defining and computing differences is a very difficult task. It's all varies on data sets. Therefore, whereas juxtaposition approach does not have these issues, it's the most general approach right next to the interchangeable approach. To do so, we modify and combine several techniques. Compared to portals, our technique does not do near clipping to immerse in the environment rather than feeling like you are looking through the windows. Compared to the magic lens metaphor, our lens is much bigger than the user. Compared to worlds in miniatures, we show multiple views, immersive views per multiple environments. So our approach is to be present in multiple worlds simultaneously. We do this by dividing the volume surrounding the users into wedges, like volumetric portals. But our approach of dividing the space into wedges gives us these sub-3 problems. maintaining context, system control, input focus, and navigation. Our solution is to integrate 3 levels of visualization. I've already introduced the Worlds-in-Wedges idea. We treat this as a top level of visualization, and we add 2 additional levels to this. The Worlds-in-Miniature level shows the current location as well as the data glyphs that shows the variables that are not visible in the realistic rendering. The context level shows how these worlds are connected to each other. So we apply this technique to forestry data to support the cases to compare multiple forests in the United States. So in this case, data glyph on the WIM represents a tree. The context layer is the US map. So at the start of the application, user only sees the US map, and the user selects a dot on the maps to activate a forest and its corresponding WIM. And in our technique, WIM works as a widget. So you can change the wedges with the WIMs using the US map as like a frame of reference. For instance, in this case, moving the WIM horizontally changes the order of the forest in the space. Or using the WIM like a vertical slider, you can zoom in or out the corresponding forest. Or moving WIM out of view, so below the bluish bounding plane deactivates the corresponding forest. In our technique, there are multiple forests present in a space, and you might just want to interact one specific one. To do so, you lightly point to the gigantic wedge of the world, and once that is the focus, all the user inputs are sent specific to that world. After pointing for walking, you can use your touchpad to move in the direction. And once the wand is pointed upwards, the flying mode is activated. Or you might want to interact in all the forests at the same time, like flying up to compare the heights of the trees in all the forest. To do this, you hold down a modifier key on the other wand. In this case, all the user inputs are sent to all the activated forest. So we have applied these techniques to US Forest Service Inventory Analysis data set. In our system, you can compare about 100 forests across the US. And from the data, we construct this realistic forest shown in the immersive view, as well as the data glyphs shown in the WIM. Species, height, above and below ground, carbon contents are mapped to the data glyphs. The placements of the trees on the forest is also data-driven. And this is an ongoing project with 2 scientists from the US National Forest Service Center. And we have collaborated and have regular meetings about 2 years. And I'll be reporting on from our most recent critic session, which lasts about 2 hours. So one interesting observation is that a scientist was looking at a forest in the state of Maine and realized there are like few trees much taller than the other trees. And he just looked on and then thought maybe there's an error in the system. But after pointing at the tree, which brings up this information about the trees, he realized there are different species. Like the much taller species are red and white pines, whereas the shorter ones are spruces. And he tells us stories about in these particular regions in the United States, there will be few red pines, but there will be much taller than the other trees. And he explains this, he already knew this, and this is already part of the data, but seeing in VR, in real life scales, the meaning of the data, this trend is really obvious right away, compared to looking at a data table on a PDF file. Also, making comparison, people use our technique to see how these different regions across the United States have different species, tree species. Also, there was an interesting observation made when a scientist was comparing 2 forests. on one forest, trees were, looks like a regular forest where trees were similar heights and stuff, but on the other forest, there's a clear boundary where trees on one side was much lower than the other side. And then the scientists start telling us a story about that forest might be a tree farm where people harvest trees, which putting this forest in one space really highlights the differences, and then also provides a powerful conduit to tell these data-driven stories, which led us to having a discussion of the potential of using this system for public-facing storytelling tool. So our work is applied to a forestry data set, but we like to apply it for other spatial data sets. Of course, we want to do more formal user evaluation. For instance, in our system, do user feels they're looking through the windows compared to really be present in this spatial environment? Also, if that is so, how do you measure that? And also, if each environment have this unique background sound, how do we merge? So this is a picture of Istanbul, and this is a very unique place because it shows two historical sites. On the top left is the Hagia Sophia, which symbolizes Christianity. On the bottom right is the Blue Mosque, Islam. When I visited the city when I was young, this was very interesting because these two religions seems two polar opposites, and seems to fight every day. But standing on the street, seeing left to right these two historical sites, makes me realize they're really closely connected to each other. And this kind of insight and question I wouldn't be able to gather if I was in Vatican City or Mecca, for instance. And in VR, we can create any kind of environment. We can create this kind of environment where helps us to ask these kind of questions and provoke curiosity. And as a conclusion, Worlds-in-Wedges provides a comparison approach of the data analysis in VR, which is done by combining several techniques like photos and WIM. And this is applied to scenarios of comparing multiple forests in the United States and shows promise to comparing other data sets in other domains. I want to acknowledge fund providers as well as a student who helped with figures and videos. Thank you.
So thank you for your presentation. Do we have any question?
Brett Jackson, McAllister College. Thanks, Jung. That's interesting work. Could you elaborate a little bit on the user experience? I had this interesting thought when I first saw it that it might make people pretty sick, but then particularly when I saw the video of you just navigating one of the portals, you essentially have almost a reduced field of view, which has been found to reduce simulator sickness during navigation. Have you thought at all about how that affects working with this?
The reduced field of view with the cyber sickness and stuff. I mean, this, of course, we have to do formal user study, but by looking at observing people who have tried it, have not made any complaints about this, especially when you're moving in one forest at a time. Yeah.
That's interesting. Thanks.
So I have a question. Well, it's not a question, just a thought. I see some very interesting potential in this approach for some collaborative work. Did you think about it, or try some pilot study?
Yeah, that's super interesting. So you can imagine the forest being different locations and the different collaborators. Yeah, we thought about it. I mean, we didn't mention anything about it in the paper, but like I said, we apply this to a forest, but it can be applied to any other environment scenario. And I guess collaboration is one of them.
Okay, so let's thank again our speaker.